Okay. Then the last talk for this session, we have Rafi from Samsung, who is going to talk about taking AI to the edge.
So hi everybody, my name is Rafi Dalla Torre. I'm heading the advanced research group at Samsung Research Israel, and we are sitting in Herzliya. And my talk is a part of the work of also a few people from my team. We have Matan Wexler, Benjamin Lastman, and Ben Gordon. So thank you for them for being part of this work. And my talk is divided to 3 parts. In the first one, I will answer to the question why. Why do we need that? Second one is how can it be achieved? And the last thing is what is our method and what is new in what we are proposing. So let's speak about why. Why taking AI to the edge? So all the edge devices, and especially for Samsung as an edge company, offer many AI capabilities. For example, if we have a keyboard, or if we have a camera, or if it's a smart speaker, that is also something that Samsung is developing. AI capabilities like autocorrection or autocomplete for the keyboard, or image enhancement, or face detection, or either it's speech-to-text that is on smart speakers. Everything requires AI capabilities, and the way that actually it's working is by sending the data to the cloud. And this kind of architecture is called as cloud AI, and it's the most popular architecture. And this is kind of most applications or most edge devices are not smart devices, but actually devices that are connected to a smart cloud. As you know, the trend is to moving to the edge AI or on-device AI, moving the AI capabilities to the edge device. And this is something that is happening everywhere. And it's very important for Samsung as a company developing edge devices. So let's speak one slide about why. The advantages are, first of all, privacy and data protection. In the cloud AI, we need to send all the data to the cloud. In edge AI, we're keeping the data in the edge itself. So in terms of privacy, it's much better. Also in terms of data protection for an organization, not sending all the data to the cloud, that who knows what would happen to the data. The second advantage is the fact that actually cloud AI would require network connectivity, being connected to the cloud itself. So in places that we don't have network connectivity, that's an issue, and also latency due to the connectivity issues. So for example, smart cars, autonomous cars, that's an issue to connect them to the cloud. And the last point that probably is the most important one is actually operating costs. So for cloud AI, the operating costs are on the cloud side. So for example, for Samsung, we would need to invest a lot of money in cloud computing, rather on edge AI, all the computational is done on the device, so actually the cost it's much, much smaller. So this is one of the triggering point for edge AI or on-device AI. So after this short introduction, let's speak about how this can be achieved. So the deep neural networks become bigger and bigger and bigger, and there are many challenges. So if we look at that from Samsung as a company developing edge devices, the issues so if we speak of that as Samsung is developing edge devices, the issue is, first of all, memory. If the deep neural network, as we can see here, becomes of hundreds of millions of parameters in case of vision, that's an issue for memory, from memory point of view, and also from computational point of view, flops. That's a big issue to do inference on edge devices. And the third thing is battery. So battery is something that all the edge devices are constantly struggling to increase, and having big neural networks on edge, that's also a challenge in terms of battery. And just to give you an just perspective, so Samsung S10, the performance of its GPU is around 500 million flops. So you can see we cannot process even one example per second. So this is a big issue in terms of computational complexity. So let's focus on what are the strategies in order to achieve, in order to be able to perform AI on the edge. There are two main tasks. The first one, training or inference. And there are two main aspects, algorithms and hardware, dedicated hardware. So in my talk, although we are in the hardware track, we will present a way to do that is hardware independent. So it doesn't require putting dedicated hardware. And it's based on algorithms, on algorithms that can make deep learning more efficient. And we are focusing on inference because this is the biggest problem, because in terms of scalability. So let's speak about the two main approaches. If we want to have a more efficient deep learning network, there are two main approaches. The first one, it's called, it can be called knowledge distillation, but actually it's training a smaller network. So for example, the teacher-student architecture, we have a big neural network. So assume that we have a big deep neural network that is already trained. We want to achieve to have a smaller one. We can train a smaller network using soft metrics from the big network. So this architecture or this approach of knowledge distillation looks very good, doesn't work that well. So, and it also is limited in terms of performance. So the second strategy that is more common and we are focusing on, we call it, it's kind of model compression. So it's taking an existing deep neural network and reducing its size. In this case, as I told before, we would like to reduce the computational complexity, the memory, and also the battery. And something that should be taken into consideration, that what costs much, much more in terms of battery is accessing memory. So computational is not that, doesn't consume a lot of the battery, but memory accesses consume much, much more, as you can see in the graph here. So this is something to take into consideration. And as the previous talks described, there are a few algorithms how to achieve model compression. The first one is weight pruning. The second one is quantization, like Professor Daniel Suri was describing. And the third one is low rank approximation. So let's discuss why these solutions are not good for us, for our needs, and what we are proposing instead. So the first one is weight pruning. So weight pruning, it's something that is related to removing small weights. So in case that we have we have some parameters, some weights that are very low, we can replace them by zeros. And this can reduce the number of parameters. But if you look into the hardware itself, what we are creating, so this is kind of an example of performing pruning. We are removing the weights with low values, keeping just the higher one. It's also called thresholding. What is happening that we get a sparse matrix. So if every network can be represented, for example, a fully connected layer can be represented as a matrix. Removing part of the weights would mean that actually we have a sparse matrix, a matrix with many zeros. And a matrix with many zeros, we require a dedicated hardware to do the multiplication in order to really have, any efficiency gain. So in our case, we would like to offer capabilities of deep learning, efficient deep learning without requiring specific hardware. So, and without requiring solutions that would, for example, zero skip can take advantage of sparse matrix. So this solution is hardware dependent and doesn't work for existing devices that don't have specific hardware in them. Second option is quantization. So quantization, I will not describe it, it's quite trivial, but low bit representation, we can take just a few bits, we can use binary or ternary representation. There are other ways in order to achieve quantization, for example, weight sharing, having many using a code book, Huffman encoding of the weights themselves. All of these solutions would require dedicated hardware that would support working with weights with only 1 or 2 bits. Or, for example, if it's related to, for example, code books, we would need software packages that would support that. That is something that is not that common. So also quantization is an issue if we want to do efficient AI or efficient deep learning on edge devices. The third thing, surprisingly, is a good solution, and it's a low rank approximation. So if we take at the bottom line, performing low rank approximation is taking one operation and splitting it to two simpler operations. So taking one layer and splitting it to two simpler layers through kind of separability. So for example, for the fully connected layer, which is a 2D matrix, we can perform an SVD and get two smaller matrices, or we can even do two convolutional that are only 1D. We can do the same for convolutional layers and achieve, like for example, MobileNet is doing that. And what we like about this solution, that is hardware independent, because the building blocks are exactly the same building blocks that we used at the beginning. We are constructing a simpler 2D convolutional layer. We are splitting a convolutional layer into two simpler convolutional layers, the same building blocks. So this is a very good solution, and we are inspired by this kind of approach. And another thing that is very important, there is no one algorithm that solves all. It's always an ensemble of algorithms. We need to combine many algorithms together in order to achieve really deep learning efficiency in the edge device. For example, this is a very popular slide from Songhan work showing that we need to do pruning, quantization, and Huffman decoding, and only by that we can achieve efficiency in, for deep learning in edge devices. So another thing that we keep in mind, we need a method that would work as part of an ensemble of other methods, because our method cannot solve everything. It must be a combination of. So what is our method? So let's have a look at a few things. So first of all, as I've said, we want an hardware-independent approach. We don't want our solution to be to require specific hardware, because we want to support all devices or existing edge devices. Second one, it must support working as an ensemble of methods. And let's look at a few things. When we look at the complexity of any deep learning network, it's related to the number of parameters, number of neurons, or number of filters in case of convolutional layer. Another thing is actually that reducing the number of filters on neuron is a very good thing, because it's maintaining the structure. We are not creating any sparse matrix, but actually, for example, we are removing a few lines. Or in case of reducing a number of filters, we are still keeping the same structure of convolutional layer, just with less filters, so less computation, less memory, and most of all, less battery. And another thing that we are inspired by nature, also in our brain, something very similar is happening. So the number of synapses is growing until the age of 1 year old, and then it's growing, and then it starts to decline. So this is something that is happening in the nature, finding which neurons are the most important one, and this is what we are inspired of, and we would like to do the same. But this is a challenge. Doing that for weights, we discussed that before when we discussed weight pruning, it's easy. Because for each weight, removing smaller weights, if a weight is very close to 0, replacing it by 0, that's not a big issue. So for example, you can see, for example, we took a VGG19, we looked at the fully connected layer, and the weights, they behave exactly as we were thinking. As the Gaussian distribution, we can remove the smaller one. That's easy. How can we do that for neurons? So let's look at neurons. Any neuron, for example, for the fully connected layer, actually it's a vector. It's a vector of parameters. What we discovered that if we look at L1 metrics per neuron, taking just the strongest one, doing thresholding, that's wrong. Because L1 would always be positive, and the strongest one are not the most important one, or not the most relevant ones. So let's look at an example. We took VGG19 again, look at the fully connected layer, and we have 4,096 neurons, each one with the same number of weights. And this is a distribution of the L1 metrics per each neuron. The approach that we are suggesting and that we have tested is using the representation, using representative neurons. So in this case, you can see here, if this is the distribution of the neurons according to L1, we decided to took representatives according to this distribution, which is the red circles, and just take a few representatives. It's a weighted representation because neurons that are here actually would replace many neurons that are very most popular. So we want to give them a higher weight rather than the neurons that come from the sides of this distribution. The same can be applied also for convolutional layer. For each filter, we can perform the L1 metric per each filter. And again, draw and distribution of L1, it will be also be Gaussian. We can take, again, just representatives. And according to the compression rate, we can decide how many representatives we can take. And surprisingly, this is showing very good results. So, for example, for VGG19, very easily, we were able to compress it 7 times with no degradation. And now we can do any kind of additional ensemble method because we didn't change anything in the structure of the network. So now we can do quantization. If we have dedicated hardware, we can do pruning. And having a dedicated hardware that can take care of this sparse matrix, this is something that would work. If we want to do Huffman encoding, that's okay. So everything would work well. What is also very interesting about this method is looking at the performance of this method. So this is a graph showing the accuracy versus the compression rate. So if we try to take just the strong neurons like we did with weights, this would what happened. There are many ways to calculate the L1 per neuron. Maybe taking just the weights, the entry weights or the output weight, the input weights or the output weights or any kind of a combination. That doesn't work. So if you can see here, for small compression rates, that would work. But as soon as we start to compressing it deeply, then the accuracy would drop and completely collapse. So what we discovered about our method is that using our representative method, we can compress with very high compression rates, no degradation, almost no degradation in accuracy. And what is more interesting, that the accuracy is not collapsing. It's dropping, but it's not a free fall. So this is showing the importance of how strong the representative neurons method or representative filter method that we have tested. And how strong it is actually to achieve very deep compression rates. And to conclude my talk, so this surprising compression method works very well. Can work, it's hardware friendly, doesn't require any specific hardware, any dedicated hardware. Second thing, it can be part of an ensemble, as I've discussed. You can do any additional compression, and that's maybe the most important message from my talk, that everything that you're developing must be a combination of an ensemble. There is no one algorithm that suits all. And in our vision, what we are working currently, and this is the biggest question, which kind of budget are we allocating for each layer? This is something we are working, and we see a vision in which we can do an automatic compression. So finding the optimal parameters, how many filters and how many neurons to keep in each layer in order to achieve the best compression and still maintaining the accuracy. So this is the biggest challenge that we are working currently, and everything will be based on this neuron representative methods. That's it. So if you have any questions, we'll be happy to, yes.
Why is your method not dependent on the hardware?
So that's a good question. If we look at, for example, a fully connected layer, we can represent a fully connected layer as a matrix, okay? If we perform any kind of, if we remove just a specific weight, now we get a sparse matrix. So that's it's a different matrix. Or we treat every zero as if it's a normal parameter, so it's not shrinking. Or we need a specific hardware that can treat zero differently. For example, skipping zeros, so we don't hold them in the memory, and we don't perform any calculation. So we get any advantage from this zero. If we remove an entire row here, that's equivalent to removing a neuron. So, and having a network with one neuron less, that's normal. It's not an issue for any software-based solution. We don't need any hardware to support that. We just we just by that design a smaller network with less neurons. In this case, in case of representation, we just have a matrix, a normal matrix, but with one row less. Yes?
How do you decide which neuron you remove? I mean, I saw the histogram and you chose representatives all over the histogram, but how do you choose the specific afterwards? The specific neuron that you leave or those that you know?
So this is one of the most important things, how to decide which representative out of all of these that are in the same area. My suggestion is try and error. So because we are doing that offline, you can do that several times until you get a good representative. This is my best suggestion to do. By that you can have a very good representative. Without doing that, you will get nice results. But you can improve by retrying, and it's not an issue, right? You're doing the compression offline, on the cloud. You just want to have a smaller network and the best one. So a few trial and errors would work. That's not a big issue. Yes?
Simple question. The Pruning is open source and you've got this methods.
Not yet. So this is what we're showing is still under heavy research. So this is something that we are planning to publish in one of in the near future, and after that it will be also company level use as the source. But stay tuned. Any other? Yes?
You changed your normal convolution layers to separable convolution?
So in this case, you're speaking about the low rank approximation. That's a normal thing that it's changing, like replacing a complex convolution by two separable convolutional. So I'm not speaking about what mobile net are doing. That's another thing. In this case, what we are doing is we are just removing a few filters. So the same thing that we did for neurons, our method is based on finding the best filters. We're not, on top of that, you can do what you just said, on using any kind of low rank approximation. That's not an issue. You can do that. It's a kind of, any solution will be an ensemble of methods. So you can use our method, find the important filters, find that they're just a representative filters, and that's it. You have a smaller network. Now you can do any kind of low rank approximation that is based on replacing complex convolution by smaller or simpler convolutional methods. There are orthogonal methods, and they can work one after the other. So that's the importance of what we are doing here. Maybe I would add that we tested our method. Also, if you're doing, for example, you're doing pruning and then you want to use our method, many of the weights disappeared in the neurons. So we discovered it works. It works even if you have many zeros, even if you do already pruning on the weights. Yes?
So if I understand correctly, you're not dealing with the training phase, only with the predictive, right?
Exactly. So the training phase, it's not an issue of scale. It's an issue that is actually maybe just the people in this conference are worried about training time, while inference time is something that every user is worried of. So in terms of scale, we are focusing on inference. It's a problem of hundreds of millions of users, while training time, it's a problem of, I don't know, a few hundreds of engineers and researchers, or a few thousand that are less important. More expensive, but less important. Yes?
You showed the results earlier of, I think it was 7x for VGG.
Yeah.
But VGG is a bit of a heavy network, or over fat network.
Yeah.
Right? You have results for other, like ResNet or Inception networks?
We have, but not for this presentation and not to be published yet. But that's a good question. We focused on VGG because it's kind of a benchmark that everybody is focusing and showing results on. So if you look at all the articles in compression, they would show results on VGG and CIFAR10. And so we wanted to show some results that are kind of aligned with what other articles are showing. We have results on other networks. We see also very good results on other kind of networks. We also started to look on NLP models, but not public yet. Yes.
Do you do several iterations when you remove the filters, or is it just in one pass? I mean, do you remove several filters and then you need to retrain your networks and then you do another pass, or just you do one time you select several representative filters and you remove all the rest and that's it?
So doing retraining or fine-tuning is always the best practice. This is what I suggest to do always. In this case, we can do it in one pass. We can just find the representative and then doing any kind of fine-tuning. We believe that doing it in iteration would not be that dramatically different. So it's easier for us to do it in one time and doing the retraining only once and not every time in terms of efficiency. Okay, thank you very much.